I thank the organizer for organizing the international virtual conference, GeoVartex. This virtual platform gave us opportunity to interact with our students and fellow colleagues all over the world. So thanks to this virtual platform, and thanks to UDGS and Kurukshetra University of Geophysical Society for inviting me for this GeoVartex seminar and conference. I hope this virtual conference will lead to a successful collaboration among the geoscience students of India and Bangladesh. So I have been working with the Lamont Doherty Earth Observatory of Columbia University for nearly 2 decades. Now it's 2 decades on crustal dynamics, earthquakes, and natural hazards. Our collaborative project is being funded by NSF, ONR, that means Office of Naval Research, NASA, USAID, and we receive instrumental support from IRIS, which is known as the Incorporated Research Institution for Seismology, and UNAPCO. UNAPCO is a consortium of several universities and is responsible for giving loan to instruments, especially the GPS. So tectonically, Bangladesh sits at the junction of 3 plates: India plate to the west and southwest, Tibet subplate to the north, and Burma sliver to the east and southeast. Moreover, the plate boundary between India and Bangladesh passes through Bangladesh. The eastern half belongs to the Burma plate, and the western part belongs to the India plate. Shillong Plateau, also called Shillong Anticline, is considered as microplate within Indian plate by many workers and is moving southward direction. In fact, this 2-kilometer high Shillong Plateau is the forward jump of Bhutan and Sikkim segment. Let's have a look at the video clips, how the Indian plate collided with the Asia and give rise to Great Himalaya to the north and Burma Arc to the east. So this animation was actually prepared for our project funded by National Science Foundation of USA. And we made a documentary film on earthquake hazards covering Bangladesh, Northeast India, and Nepal. So Bangladesh occupies major part of Bengal Basin and entirely sits on the Ganges-Brahmaputra-Meghna Delta, which is the largest in the world. The Ganges and Brahmaputra River drains most of the Himalayas and supply over 1 billion tons of sediment to the delta each year. Delta is very dynamic with rapid sedimentation and high subsidence rate. The formation of GBM delta and its southward progression is the interplay or interaction of sedimentation, river dynamics, and this two convergent plate boundary. And this is the conceptual geodynamic model of Bangladesh and surrounding regions, showing the major tectonic elements. About 88% of the country is low-lying flat landscape with 19-kilometer thick Cenozoic sediments. The rest 12-kilometer landmass in eastern Bangladesh and its continuation further to the east in northeast India and Myanmar represents tertiary hills known as Indo-Burman hill range. The tertiary hills are characterized by 250-kilometer wide and 1,400-kilometer long accretionary prism resulting from the oblique convergence of India-Burma plates. The accretionary prism is deformed into a series of north-south trending N-echelon folds and thrust faults. It marks the plate boundary between subducting Indian plate and overriding Burma plate. And it's a landward northern extension of the Sumatra-Andaman subduction zone. The westernmost structures along the shore are faulted down and form a long escarpment right from the Chittagong to the Teknaf. The fold and thrust belt evolved through a process of two generations of deformation, firstly during Paleocene in Myanmar, Mizoram segment, and secondly during late Neogene in Chittagong, Tripura segment. The anticlines of Paleocene deformation is very close, tightly and intensely folded, whereas the anticlines of Neogene deformation are widely separated by broader synclines. The Paleocene and Neogene structures are separated by Galadan fault, which represents the old deformation fault or the old plate boundary. The deformation advances westward into the deltaic Bangladesh, and the deformation fault runs near the low elevation Meghna estuary to the south of Sunamganj, Kishoreganj, Haur. So this is the deformation fault that starts from the Sunamganj, Kishoreganj Haurs and meets with the deep channels of Meghna and goes south into the Bay of Bengal of the shore of the coast down to the Sumatra. And this is the conceptual geodynamic model of Bangladesh and surroundings showing the potential source of major faults. So this is the Himalayan frontal thrust that starts from northwest syntaxial bend and ends at the northeast syntaxial bends, which is about 2,500 kilometers. Then another plate boundary is started from this northeast syntaxial bends and runs down to southern Sumatra, which is 3,500 kilometers. And we have a Dauki fault, east-west Dauki faults, which is a high angle thrust dipping towards north. Another is an offshoot of Dauki fault, which is called Dapchi Falls, which is exposed in the Shillong Plateau. And it runs through the alluvium plain, hidden under the alluvium plain in Bangladesh. And it's likely or supposed to be joined with this Himalayan frontal thrust. We are not sure about this, but we have a GPS. So in future, we can tell with a positive way that if it is a continuation of these Dapsi faults beneath the alluvium plain. There is a plate boundary faults, Sylhet Assam faults, and also the Arakan fault system. Then in the fault belt, there is a Kaladan faults, which I say it is a old deformation fault or the plate boundaries, or paleo plate boundaries. Then there is a Kabua faults and the Sagain faults. And these faults are very active and seismogenic and produce earthquakes in the last 400 years. So the first major earthquakes in the record was occurred in 1548, and it was a terrible one and destroyed Upper Assam, Sylhet, and Chittagong, and brought changes in the landscape of these regions. So I'm just telling about the major earthquakes, not the minor ones. The details of the earthquake and the damage are not available, but it opened numerous ground fissures and caused liquefaction in Assam, Sylhet, Tripura, and Meghna floodplains. It is assumed from the description of the reports that 1548 earthquake epicenter was somewhere in Upper Assam or Nagaland. The earthquake of 1762, which is located along the Arakan coast, and it occurred on the 2nd of April in the afternoon of 5 p.m. with a magnitude of 8.5 plus that ruptured about 400 kilometers of the Arakan coast from the Teknaf down to the Yangon. This earthquake was very destructive and violent, felt all over Bengal and Arakan. About 500 people died in Dhaka due to boat capsize and washed away the houses situated along the river banks of Buriganga River. The earthquake produced uplift of 3 meters on Saint Martin Islands, 2.7 meters on Foal Islands, and 6.7 meters on Chidua Islands. These Foal and Chidua Islands are located in Myanmar. And submergence some areas of Chittagong and the coast of Chittagongs. This 1762 earthquake generated tsunami in the Bay of Bengal. And this 1787 earthquake, which is located in the western part of the Shillong Plateau, was also very severe, but not much is in the history or in the literature, but peoples of that generations, they notice a change in the course of river Brahmaputra, which was flowing through the Mymensingh, is now flowing along the Jamuna, present Jamuna River. So the major earthquakes can change the landscape recorded in the sediments or geologic history. The 1897 earthquakes, this is also located in the Shillong Plateau and is known as the Great Indian Earthquakes, which occurred on 12 June of 1897 at around 5 p.m. on the Shillong Plateau, which is about 200 kilometers north of Dhaka. The magnitude was 8.7 and one of the most powerful and destructive earthquakes in recorded human history. The earthquake was felt all over the subcontinent and it ruined 390,000 square kilometer area, and most buildings in the Shillong Plateau and its surrounding regions were grounded. Extensive damage from shaking and liquefaction occurred in Assam, Meghalaya, and Bangladesh. 1626 people were killed. Then there is 1950 earthquake located in Arunachal Pradesh along the borders of India and China. It had a magnitude of 8.4 on the Richter scale and struck a relatively sparsely populated region in Arunachal Pradesh. The earthquake triggered on 15th August at 8 p.m. and felt all over Bangladesh. And students of the dormitories of Dhaka University, they rushed out to open space for safety. Water bodies in Dhaka and other parts of the Bangladesh remain agitated for an hour due to the long period effect from the distant earthquake. Then in recent times, in Nepal, an earthquake in Gorkha is known as Gorkha earthquake occurred on 2015. And it had a magnitude of 2,000 people, including 3 people in Bangladesh. And this earthquake was located more than 700 kilometers from the capital city, Dhaka. And 3 people were killed due to panic and stampede. So it is very significant to note that most of these earthquakes, mega earthquakes, were occurred during the monsoon time and post-monsoon time. So there is a relation of releasing energy due to water loading during heavy monsoon period in this Bengal basin. So the seismogenic force at some segments has released strain energy, but at other segments, the energy is yet to be released. This led to seismic gap and has been demarcated by a red color. Bangladesh has 2 potential threats of major earthquakes, one at the eastern segments of Tauki Fault, and another is the Indo-Burman subduction zones to the east. And both these sources, 2 sources, are very close to Dhaka, which is 50 to 100 kilometers, few hundred kilometers. And this subduction zone earthquakes is very notorious. And this is a seismicity map of Bangladesh and surroundings. In general, Bangladesh is a country of low seismicity. You can look at this map. All the epicenters are located in the Paleocene deformation system. And very little earthquakes epicenters is located in Neogene deformation or in Bengal Delta plain. So the Neogene deformation system of Chittagong Tripura fault that has little or no seismicity. And this indicates a state of locked condition of the plates. And if you look at this index, so there are the deep focus earthquakes, which indicates a bending of the subducting Indian plates. So the plates very gently dips up to this position, and then bends around this 94-degree longitudes, and this turns very dips here. Though Bangladesh sits at or near the junction of 3 tectonic plates, yet it demonstrates low to moderate seismicity. Why? When an earthquake occurs in Indo-Burma fold or belt or the Himalayan belt, the media people rush to seismologists and they publish reports in a way that panic people. And also when we try to bring the significance of earthquake study or earthquake science to the importance of the earthquake study to the bureaucrats, government officials and planners, and to the politicians, They says that they haven't seen big earthquakes in their lifetimes. They haven't heard of it from their forefathers. So why we are creating panics among the peoples? So let us try to explain why this zone has little earthquakes and how it could lead to megathrust earthquakes. So as I said that these neogen systems in Bangladesh, that is in Sylhet, Tripura, and Chittagong, and seismicity. So what is the reason behind this? And just to the east, in the same fault belts, it has a very significant earthquakes in recent past or in historic past. So why there is a marked difference between the seismicity in these two deformation systems, that is in Paleocene system and one is the Neogene system. So we'll try to explain so why there is very little seismicity and whether this little seismicity is a threatening to the people of Bangladesh and also to the Northeast and Myanmar people. So in order to see the earthquake behavior pattern and the plate motions, we have installed 25 GPS. We started with the 6 GPS station marked at the triangle sites in 2003. Then over time, we install, in total now we have a 30 GPS covering mostly the eastern parts, the coastal parts, and the fault belts of Bangladesh. And this animation demonstrates movement of land using GPS technology. Usually, the slow movement at any point is invisible to us, but GPS can record this movement, slow movement. So GPS and other geodetic tools can precisely monitor and record the every incremental change in position of the land. GPS or other geodetic study can precisely record the change in position. It shows how a typical sawtooth pattern of time series is related to build up and release the energy. So in this graph, time series graph, so due to the motion of this land, the energy is being built up within the crust until this time. Then when it exceeds the friction energy, it just releases at these points. And then again starts building up new energy and continues for few years and then again release. And so this is a seismic cycles. So at some regular intervals, the accumulated energy release. And this is happening for every earthquake, especially in the subduction zones. So we'll be concentrate on our subduction zones in the Bourbon subduction zones. And the next slide is, and this slide has been prepared by the Incorporated Research Institution for Seismology based on the study of Cascadian subduction in North America. And the next slide also shows a typical movement of the subduction zone in Cascadia subduction zone. So this is a typical subduction zones prepared by this incorporated research institution for seismology. And there are 3 GPS installed on 3 segments of the subduction zones. This first one is set on the log zones. So here these 2 plates, subducting and overriding plate, is locked here because this is a shallow and it has a very high frictions. So due to the low temperature, the friction increases and it's locked with the upper plates. And extreme right, the subducting plates bends down, and this at this interface, the pressure and temperature is very high, so the rods becomes very ductile and has very little or no friction energy. So it cannot hold the plates. So when it pushes from the right and up of the upper plate and the underthrust and the subducting plates pushes downwards, it cannot start or hold with each other and it slips. But in the middle parts, this is also the depth of the interface is intermediate and the temperature is relatively high, but still has a frictions energy in the plate interface. So it can hold energy some little, but when the energy exceeds the friction energy, it just jumps. So it is reflected in these graphs that at every 14 months, this energy builds up, then it's pushed backwards, yeah, and starts again its build-up of energy. So this is called a episodic slip or slow slip earthquake. But at the leading edge of the plate, where the 2 plates are locked or coupled with each other, there it indicates there is no release of energy and continuously builds up the energy. And it will continue build up the energy until it exceeds the friction energy. So we can understand from this animation that in the middle part, where there is a slow slip earthquakes, energy can hold for a few years and then releases energy. So the magnitude is also not so great, might be strong, but not so great like the locked zones. And since the locked zones is being receiving energy for long periods, even for over 1,000 years, so it has an accumulated strain which can lead an earthquake of magnitude more than 8. So that's why this subduction zone earthquakes is very notorious. And this is exactly this phenomena is prevailing in our Indo-Burma subduction zone. So this is a GPS at the rooftop of geology buildings, which was installed in 2003. And these are the 3 components. This upper 2 is the horizontal components, and the lower one is a vertical components. So this horizontal 2 component shows a very steady growth of energy or moving land motions, but the vertical component shows a sinusoidal. So that means it is an elastic deformation. And if you look at this pattern, when the curve goes down, it is around that monsoon times when the monsoon starts. So starting bending down, that is around April, May, the curve goes down. And when it reaches the peak times, when the monsoon is peak times it has a maximum down, then slowly goes up when the floodwater goes away to the Bay of Bengals. But on a on an average, the land is subsiding at 12.23 millimeter per year. And this two horizontal, which has a steady growth of strain energy, is moving towards northeast. This is the Dhaka station is moving towards northeast. And this is a velocity profile, velocity, GPS velocity of Bangladesh, Northeast India, and Myanmar. We possess our GPS data along with the campaign station of Myanmar and the published data of the Northeast Indian study segments. This blue colors indicates the published data of Northeast India. This green color indicates the campaign stations, GPS stations of Myanmar, and this red arrow are GPS from Bangladesh networks. So in the next slide, we'll see the change of ground motion in velocity profiles. So with respect to the Indian plates, fixed, the motion of the Myanmar part and the Mizoram parts is shown here. And if you draw a profile along east-west, that is the fold belt perpendicular and fold belt parallel, we'll see the velocity of this GPS. So where is the velocity profiles across the fold belts and fold belt parallel. So this one is the across the fold belts. It is the convergence, and this one is the dextrals. And this is the profile. It shows the subducting Indian plate and overriding Burma plate. And we have calculated the total oblique motion is 46 millimeter per year. And since this Indo-Barban subduction zones has a thrust fault as well as the strike slip faults, the total oblique motion 46 millimeter is being partitioned along this thrust and shear faults, that is strike slip faults. So whereas this one is the subducting components, and this one is the Churachandpur Mao fault, which is located in Manipur, and then the Kabua faults, which is the intersections with the Burma fold belts and Burma central basins. And to the far east, there is a Sagain fault, which consumes much of the energy of this 46 millimeters. So only about 15 to 17 millimeter per year energy is being consumed by the convergent motion of the plates. Based on the GPS velocity profile across the subduction zones, demonstrate that the delta plane and the Chittagong Myanmar fold belt has shortening rate of 15 millimeter per year, which is partitioned in 2 millimeter in delta plane, then 5 millimeter in Neogen systems, and 8 millimeter in Paleocene system, deformation systems. The Chittagong Tripura segment is locked as this zone has little seismicity and low GPS velocity with steady increase of strain energy. The Mizoram Myanmar segment has periodic seismicity. The cartoon animation demonstrates how the log and slow slip zones behaves in subduction zones. Similar phenomena exist in other subduction zones, particularly in Cascadia subduction zones in North America. So we have calculated the amount of strain energy that is being stored in these log zones is equals to 8.2 to 8.5 to 9.2 magnitudes. And the capital city Dhaka is very close to these subduction zones. So we don't know when this lock zones will unlock and the energy will be released. But if it releases, it will have a devastating impacts on the entire deltaic plains of Bangladesh as well as the Northeast India and Mizoram. So the energy released by the slow slip or periodic earthquakes in Mizoram segments is transferred to the Chittagong Tripura lock segments. At the same time, the northeast moving Indian subcontinent plate imparts energy to the locked zone as well. So these locked zones, which stretch from the Sylhet and down to the Myanmar, that is the Neogen systems, it receives energy from the northeast moving Indian plates and strain release by the slow slip zones of the Indo-Burman ranges. And these are the two imageries. One is from the 1989 and 2010. Shows the 400-year-old city is going very fast with an overburdened population of 18 million. And the expansion and urbanization are unplanned and uncontrolled. So these are the buildings in South Dhaka, that is the old Dhaka city. And buildings are mostly brick masonry with weak and faulty foundation. And in recent times, multi-storied fancy buildings are being constructed in low and earth-filled areas which are susceptible to liquefactions. Newly constructed, many buildings collapsed without any jolting. Roads are very narrow, little or no open space for shelter after any natural hazards. So rescue operation will be very difficult in the event of devastating earthquakes from either from the Dauki faults or from the subduction zones. In recent years, Dhaka jolted several times from local and distant earthquakes. People got panicked. Earthquake preparation is very slow. The people are now very concerned and interested to know how to cope with the earthquakes with the built environment. They want to know how safe Dhaka is. This is a log zone, and this log zone, this red color, was ruptured long ago. We don't know when it was locked, but we assume it was. We assume that rupture in this zone, rupture might have taken place about 800 to 1,000 years ago. And since the deformation is advancing towards west, we assume that the next rupture will take place along this Sunamganj, Kishoreganj, Haor, and the Meghna, that is the present deformation forms. So if this log zones rupture and the energy which is being stored for over 800 to 1,000 years, and which is estimated about 8.5 to 9.2 magnitudes. So if it's decoupled, that means unlock, so these segments will jump forward to 15 to 30 meter towards west. And this is the night vision's image showing this Dhaka city night times, how big is the city. Then this Tripura, then this is the Shillong, Guwahati, this is Shillong, this is the Chittagong. So we presume that this red part was ruptured about 800 to 500, 1,000 years ago. And there was a river, which is now the Meghna River is here, which was flowing along the foothills of this Indo-Barban range. So about 800 to 400, 1,000 years ago, this area was ruptured and the area was uplifted, and the river Meghna was advanced to 20 to 40 kilometers towards west. So there is a remnant rivers in Brahmanbaria called is the Titas, which is the dead rivers. So we are trying to date these sediments of the basal part of the Titas rivers. Once we get the dates, we can precisely tell that this area was ruptured at what times. So if we can determine the age of these rupture times, then we can tell how much energy is being accumulated in these regions and what magnitude of earthquakes can occur in futures. So whatever may be, even if we consider this is say 400 years energy is being minimum energy is being stored that can rupture, that can jump these zones to 15 to 30 meters towards west with the magnitudes of 8.5 plus. So the question is whether this accumulated energy will be released in a single event or it will release in a multiple events, which is very difficult to say. And we need more research on this. And the next, this is the cartoon of whatever I talked with the last few slides. So this is the sum up of all the geodynamics models. This is the first deformation was here, then with time it proceeds towards the west, and presently it is likely to rupture along this. And this is and that means the deformation is advancing towards west. And this is the long chance. And are we prepared for the next great earthquakes? And with this, I end my presentations. And thank you very much for your patient hearing.
Thank you, sir, for your wonderful presentation. And we have learned a lot of things from your very much informative demonstration and animation.